on the third day of the Chennai Symposium. The chair for the session is Professor Satya Prakash from Pennsylvania State University. Over to you, Satya.
Thank you very much, Sriram. Hello, everyone. Good evening or good morning, depending on where you are. Today's session will span from nanohertz to kilohertz gravitational wave observations. So to kick off, we have Pratik Tarafdar, who will talk about Indian role in Pulsar Timing Array in the global hunt for nanohertz gravitational waves. Pratik, I will warn you 2 minutes before the end of your talk. Please go ahead. 13 minutes.
Thanks.
Total. Thank you.
Thanks, Satya. So first of all, apologies for not being able to switch on my webcam. I guess there's a glitch in there, and I'm afraid if I continue using it, it might lead to a crash. So, so sorry. So, I feel really great to be finally speaking in this conference. Although an offline meeting, getting to see each other face to face would have made me feel even better. So congratulations to the organizers of this wonderful event, and thanks for giving me an opportunity to deliver this talk. So hi, my name is Pratik. I'm a postdoc at the Institute of Mathematical Sciences, and I'll be speaking on behalf of the INPTA collaboration about the role of the Indian Pulsar Timing Array in the global hunt for nanohertz gravitational waves. So basically, pulsar timing is a technique to measure the arrival times of radio signals from the pulsars. And ideally, as we know, these pulses should be periodic, which means there should be no difference between the arrival times of the subsequent pulses. However, precise measurements usually reveal some lags in the arrival times of the pulses, which are primarily due to propagation effects. And among the various delays, those due to the background gravitational waves or the stochastic gravitational waves are the ones which we are seeking here. So as you can see, as it is depicted in this image, the pulsar timing arrays are supposed to expand the observable gravitational wave spectrum to several orders of magnitude. But however, that would require sub-microsecond timing precision, which is attainable only for the most rapidly rotating pulsars, which are known as the millisecond pulsars. So basically, these millisecond pulsars are old recycled pulsars, which are spun up by accretion from binary companions. And they typically have spin periods of the order of milliseconds. So these millisecond pulsars, or MSPs as they are known, they are extremely stable rotators, and they can be considered as very precise celestial clocks. However, in spite of the accurate periodicity, the actual measurement, it is a challenge. It gets challenged by a number of delays which occur en route. And these delays begin right after the emission. Now, the pulsar is our clock, and we know that moving clocks run slow. So since most of the millisecond pulsars are binaries, the signal originating from the pulsar, it encounters various kinds of delays like the Romer delays, Shapiro delays, and the Einstein delays near the source itself. And similar delays are also encountered while it passes through the solar system as it reaches the Earth. Then the observer on the Earth is again also revolving around the sun, introducing additional delays. And again, the rotation of the Earth on its own axis, it requires local clock corrections that have to be taken into account. Now, these can still be accounted for as we have constantly updated astronomical ephemeris, which is available at our disposal. But one cannot ignore the vast expanse of the interstellar medium, which lies between us and the pulsars. Now, the signals which are originating from the pulsars, they have to cross these oceans of the cold ionized plasma before they reach us. And this leads to various kinds of dispersive and scattering delays, which are actually the trickiest delays to model. Okay, but okay. So let us suppose for a moment that we know all these delays. In that case, detection of the gravitational waves would require keeping track of pulse arrival times from an ensemble of pulsars, which ensemble is, by the way, is what is known as the pulsar timing arrays. Now, anything that is left after the subtraction of all the known delays should correspond to the background gravitational waves, which would appear in the signal as a correlated noise. Now, basically, all the PTI astronomers are now after this elusive correlated signal in their data. It has a name. It is known as the Hellings-Downs correlation. It is named after Professor Ronald Hellings and G.S. Downs. As you can see, the picture over here is of Professor Hellings, whom unfortunately we lost a month ago on the New Year Day. So it was a sad day for the pulsar astronomy community. But thanks to the hard work of numerous scientists, we now have a global consortium called the International Pulsar Timing Array, or the IPTA. It brings various organizations under one umbrella that have been monitoring PTA pulsars for decades now. Like we have Nanograph from the USA, the European Pulsar Timing Array Group, and the Parkes Pulsar Timing Array from Australia. So these constituted the IPTA until recently, when the Indian Pulsar Timing Array was awarded full membership last year. And other countries like China and South Africa are hopefully going to join in very soon. So with the uniquely high sensitivity of the GMRT at low frequencies, the INPTA data is actually ideal to study all the frequency-dependent ISM delay effects. This experiment, the INPTA experiment, was conceived back in 2015. And presently, we are observing 14 pulsars at a significant cadence. We also have plans of expansion to further pulsars in the near future. So I must emphasize at this point here that we are not bound within national or even international boundaries. In fact, the INPTA has been a very fruitful Indo-Japanese collaboration so far, along with our seniors and postdocs who are working at institutes across the globe. So I feel happy to share this picture. We are a growing family of 11 faculty members, 8 postdocs, 10 PhD students, and like 7 undergraduate students at present who are hailing from various institutes. Especially the undergrads, they receive training in pulsar data analysis at the INPTA, often as a part of their coursework. And they continue to contribute significantly to what we do. So all the data that we analyze is recorded using the upgraded GMRT telescope. Thanks to the vision and hard work of stalwarts as Professor Govind Swarup and Sudesh Thapreji, we have this marvelous interferometric array. So it consists of 30 antennae distributed in a central square and its surrounding Y-shaped arms. And the upgraded version makes it possible to conduct simultaneous observations across separate frequency bands, 4 separate frequency bands to be precise. This updated system has better receivers, higher instantaneous bandwidth, upgraded servo systems, and front-end and digital backends. So as I mentioned earlier, the interstellar medium effects are more pronounced at lower frequencies as they vary in their inverse powers. Hence, multi-band low frequency data, which we obtain from the UGMRT, is really ideal for the study of such effects. The high precision measurements of the dispersion measures, the DMs, enable better delay corrections, better filtration of the common noise processes, and thus leading us closer to the stochastic signals. The first propagation effect to worry about is what is known as dispersion. Now, the cold ionized plasma, which lies between us and the pulsar, it has a frequency dependent refractive index, as we all know. So the group velocity of the arriving signals is also frequency dependent in a way that the lower frequencies arrive later. So as you can see, this effect is clearly visible in the data. And if this effect is uncorrected or what we say is not de-dispersed, as we call it, it would certainly give wrong times of arrival. Now this de-dispersion, it requires the knowledge of the dispersion measure, some precise knowledge of the dispersion measure. So we do it using a combination of timing model fit and various regression algorithms upon the low frequency data which we have. Now that leads to an unprecedented precision in the DM estimates. Now, as a result, it helps us to even study the epoch by epoch variation of these DMs. In fact, for a solar eruption event. So there was a coronal mass ejection event which had occurred in February 2019. And during our analysis, we spotted a corresponding DM jump around the same epoch. It is very exciting that it was the first imprint of a solar event in Pulsar data.
Pratik, another 2.5
and now the next propagation effect which we need
Pratik,
to care about is called scattering.
Hello.
So the de-dispersion, which I mentioned earlier, it assumes a homogeneous interface.
Oh, he got disconnected, Satya.
Yeah, I think he was not able to hear us either. So
Yeah, we'll just wait for it.
It was just, yeah, I think he'll come back.
Hi, Pratik, have you joined us?
Hello, Sridham, am I audible?
Yeah, you are audible. For you couldn't hear us. You have a couple of minutes. Can you share your screen and continue, please?
Yeah, sure. Sorry, I got disconnected actually. So.
Yeah.
Okay, so you can see my screen, right?
Yes, we can see. Yeah.
Okay, thanks. Okay, so what I was saying is that other than the dispersion, we also need to take care of the turbulence effects, which are precisely the second propagation effects which we need to worry about. Now, these turbulence, it creates a multipath propagation of the signals through the interstellar medium. And basically, if we do not account for these propagation effects, then what it leads to is a systematic offset in the dispersion measures. And basically, it is important to account for these systematic offsets in the dispersion measures, because otherwise what happens is that it may lead to false detections of the gravitational waves. So we should remember that these delays actually mimic the gravitational wave signal, and high frequency data cannot differentiate them from the gravitational wave Hellingston downscale. So not only the ISM, but we also have techniques to deal with frequency-dependent profile evolutions. So for that, we have the wideband timing technique, in which we use fully frequency-resolved templates for cross-correlating the TOAs, basically ensuring that we compare the same things across signals, across the band frequency bands. So even higher than the traditional narrowband technique, which I discussed earlier. This is the so last year between April 16th and 17th, all the radio telescopes. Yes. This is my last slide.
Okay, excellent. Thank you. We lost your slides.
Okay, sorry. Okay, so let me end by mentioning this interesting work. So last year in April, during April 16th and 17th, the radio telescopes across the world, they observed a sudden change in one of the most important PTR pulsars known as J1713. And UGMRT was the first to observe this change in the lower frequency bands. And we also showed that this profile change actually affects the timing residuals across the higher as well as the lower bands of frequencies. We are studying this effect. We are trying to study the frequency dependent reasons behind this change, and we believe that the extraction of these frequency dependent effects would reveal the reason behind the true profile change. So in conclusion, I would say that the INPTA is a dynamic and ongoing experiment. It is expected to unravel a number of important phenomena, which are listed here. And we are presently working towards the first data release, along with some future releases to complement the other PTAs. And the community is especially looking forward to the next data release by the IPTA, as preliminary signs of detection have already been reported in the second DR. However, the most important question is whether the inclusion of the INPTA data would be able to say the final word in this respect. So we are all keeping our fingers crossed. Stay tuned and please visit our newly launched website for the latest updates. And thanks for your patience. Sorry for the interruptions. I would be happy to take questions.
Thank you very much, Pratik. I think this is a wonderful work that you're reporting. So let's clap on behalf of everyone. I'm just clapping.
Thank you, sir.
Okay, excellent. Any questions? Let me begin by asking you, how does this sudden change that occurred in this pulsar, how does it affect? I thought if it was only recent, it should not have such a big effect because the signal is accumulated over many, many years. So
no,
when did this occur and how does it affect?
Yeah, so actually you're right that if we are thinking about the noise of the common red noise, then it would definitely need some time to to pile up and make some observable effects. However, the important thing is that this extraction of the signal begins with the comparison of your times of arrivals of the pulses with some templates which you model. Now, when this profile changed, if you look at this figure on the bottom right-hand side, so these are the timing residuals. So basically, these are the differences between the times of arrivals of individual pulses at different epochs when compared to a model template epoch. So what happened is that just around the event, these timing residuals showed a very discrete jump, which you can see in this plot. And this change has been observed in the high frequencies, but what we showed is that this change is also very much prominent at the lower frequencies, which are usually which have these delay effects due to the ISM. So basically, this jump has a frequency dependence. You can see that the gap is different for different frequency bands. So what we need to understand is how this event is actually depending on the frequency, or how you can model this this event as a function of the frequencies. So that would help us to better understand whether this event was due to changes in the interstellar medium, or whether it was due to changes in the magnetosphere itself, whether it was a mode change or anything like that. So, this is going to affect the timing residuals mainly, which are essential for the extraction of the gravitational wave signal.
Okay. Thank you very much for the clarification. I don't see any other hands, but let me once again thank you and congratulations to INPTA for this wonderful work. Thanks a lot.